This is lecture 6, part 2. So in part 1, we saw this general approach called the exponential mechanism for designing an algorithm. And now we want to understand why it is differentially private. So the theorem is the following, that for every score function that is delta sensitive, so as long as the delta you're using is a correct upper bound on the score, then the exponential mechanism on inputs, the score function and delta and epsilon is really epsilon differentially private. Okay, so why is that? Well, we're just going to write down, we'll start with the finite case. So assume y is finite. And so now recall that the probability that a of x will hide all the, I'm going to drop the notation of q and delta and epsilon. We'll just, those are implicit here. So the probability that this algorithm produces output y is exactly e to the epsilon over 2 delta times the q of y given x, divided by this normalizing constant cx, where c is just like the sum of all these various factors so that everything adds to 1. All right, so now if we fix two neighboring data sets, neighboring x and x prime in our universe, and a possible output y, we can look at the probability that a of x equals y over the probability that a of x prime equals y. And that probability is equal to the, well, there's the ratio of the numerators. So we get e to the epsilon over 2 delta times q of y given x, and on the denominator e to the epsilon over 2 delta times q of y given x prime. And then c of the ratio of the denominators. So this is like c of x prime over c of x. Okay, now, what's this first term? We'll leave the second term alone for now. This first term is e to the epsilon over 2 delta times the difference between q, the quality of y on input x, and the quality of y on input x prime. Okay, times cx prime over cx. And this quantity, this thing here, this is, by definition, this is at most delta because q is delta sensitive. Okay, so that means that this whole ratio here is at most e to the epsilon over 2. Okay, and it turns out that the ratio of the normalizing constants is also going to be at most e to the epsilon over 2. So why is that? Well, cx prime, that's like the sum of e times e to the epsilon over 2 delta times q of y tilde under x prime. Well, we know that the ratio of term for term, the ratio of the terms in cx prime to the terms in cx is at most e to the epsilon over 2. So we can just upper bound this by e to the epsilon over 2 times the corresponding term for x. And so this is just the same thing as e to the epsilon over 2 times c sub x. And so what that means is that this ratio up here is also at most e to the epsilon over 2. And so the whole thing is at most e to the epsilon. Okay, so, and that it turns out is enough. Okay, so we can conclude that because the ratio of the probability that we get y on inputs x and x prime is always at most e to the epsilon, we can conclude that our algorithm is epsilon differentially private, which is what we wanted. Okay, so so I guess I skipped I mentioned what happens when y is finite. The same proof works for infinite y's. For infinite y, as long as Cx is well defined. Okay, for all x. So it has to be, for the mechanism to be differentially private, it in particular has to be like well defined on all possible inputs, and the condition we need is that like that constant, that normalizing constant, should exist for every data set x. So when the algorithm is well defined, it's differentially private. All right, so maybe it's useful to see, like, you know, why is this great? So, you know, in particular, it means that for the various examples we looked at before, we now have a differentially private algorithm, and we'll see that it does pretty well. Okay. So maybe before we do that, it's instructive to look at some other examples of, before we analyze utility, let's look at other examples. And so in particular, like maybe we can do a continuous example. So like it turns out that the Laplace mechanism is basically a special case of this general strategy of defining this general design idea. Okay, so why is that? Well, I can, for the Laplace mechanism, what's my set of outcomes? My set of outcomes is the real line. Okay, all real numbers. And what's my score function? So let's assume that I've got the Laplace mechanism with a function from like x to the n to just a single real number. So my score function is going to be just I'm going to look at the absolute value of y minus f of x. Okay, and I'm going to add a minus sign in front because I want to find a y that maximizes the score. So if I take my score to be minus the absolute value, then maximizing the score is going to minimize the absolute value. And actually, I guess this makes it maybe a more general point that there's nothing special about maximization here. We could phrase all of our problems in terms of minimization. It would also work. Okay, and then we would just add a minus sign in the definitions of the score. Okay, and so, you know, if we were in d dimensions, then this would suddenly just become the, you know, the L1 norm, just like we did before. Okay. So let's look at what the exponential mechanism would do on this. Exponential would say, you know, sample y with probability proportional to e to the epsilon over 2 times the global sensitivity of f. Yeah, so sorry, I guess what I forgot to say is that now the delta for this score function is actually exactly the L1 global sensitivity of f. Okay, so On input y, this would tell us the exponential mechanism would tell us to sample y with probability epsilon over 2 times the absolute value of y minus x. And that's like, that would be differentially private. That is indeed differentially private. It's not exactly the Laplace mechanism. So the sort of like actual Laplace mechanism consists of, we sample with probability e to the epsilon over the global sensitivity times, sorry, I forgot the minus sign, y minus f of x. And so the only real difference here is the factor of 2 that's missing here. So the actual Laplace mechanism is a little better than what you get by just plugging in the general machinery for the exponential mechanism. And that's because you're saving a factor of 2 in the exponent over the general mechanism. And in this particular case, that's because the normalizing constant like actually doesn't change with x. It's actually like the same for all x, same for all x. Okay, and so in the proof of privacy, you don't have to, this like second term here, like that goes away. And so you don't have to worry about that in the proof. And so you can sort of, that saves you a factor of 2 in the exponent. But basically it's an instance of the exponential mechanism. And randomized response, for that matter, is also. So randomized response, sort of an instance or almost an instance of the exponential mechanism in the same way. So again, my here for randomized response, my output space is a set of like vectors of length n. Remember, I produce like 1 bit per person, and there the corresponding score function is just the number of agreements, the number of positions in which the potential output and the input agree. Okay, and the exponential mechanism would tell you again to sample with probability proportional to epsilon over 2. Oh, yeah, I should have mentioned delta is equal to 1 for this score function, because if I change the vector x by 1 in one entry, then I can increase or decrease the number of agreements by at most 1. So the exponential mechanism would tell you to sample with probability proportional to e to the epsilon over 2 times the number of agreements. And it turns out that the actual randomized response, if you work it out, it's a good exercise to do this actually, to just check, it samples with probability proportional to e to the epsilon times the number of agreements. So again, in this particular case, you can save a factor of 2 because for the same reason, the normalizing constant doesn't change. So what have we done? We've come up with this general mechanism that is always differentially private. And the thing we don't really have a handle on is, when is it useful? Like, what can we prove about its how good a job it does at solving these selection problems? Okay, and so that will be the next part of the lecture.